do this. I like the idea. I like the idea of we got to win something, so that if your name gets drawn, it's just like, oh yeah, I did it, right? Okay. All right, so we're just going to keep going. We're going to keep going with these 1D problems. I think this is the last one of the 1D problems, and then we're going to go on and start talking about 2D problems, which are just multiple 1D problems, right? So this is just so fun, rocket car, right? We got a rocket car, accelerates as a function of time until it reaches 400 meters per second. Then water brakes are applied, and it decelerates as a function of velocity until it reaches 1,000 meters per second, or 100 meters per second rather. So this is going to be, again, another two-part problem that takes off acceleration of function of time, and then it turns into a problem that's going to be acceleration of function of velocity. So again, a two-part problem as we go along. On Friday, I'll show you some videos. There's some old videos of people doing this, right? They have these rocket cars to see how much G's the human body can withstand. I'll find them next time. And so they used to have this rocket car, and they go and they get up really fast, and then they hit this pond of water that then like slows them down. And when they hit the pond of water, they hit this massive amount of accelerations just to see if they could survive it. That's literally what they did. So we'll look at those. So this is a real life thing. But side note, right? I got to tell you my joke about. Sorry, this is more mechanical engineering of things accelerating and slowing down. And then we're going to do a lot of things where mechanical engineers get to deal with weapons, right? And the old saying is that mechanical engineers design weapons, civil engineers design targets. So, which I thought was pretty funny. Yeah. Yes.
Oh, I'm just saying.
Oh yeah, that's right. Yeah. But me being a civil engineer, I don't like to talk shit about it. But I will say that mechanicals, you do get to design some cool stuff. Like we're gonna see some videos later of projectiles with sabots that come off. It's so cool. Okay. Right. So we're going to start out with the acceleration portion of this thing as this thing is speeding up. And this is going to be a function of time, right? This is the first, they didn't tell us how many seconds it took. We're going to have to figure out how many seconds it takes to get to 400 meters per second. But we're going to start out with acceleration of function of time, right? This is what I was saying before, right? Like as you're learning, I don't have good handwriting, but these solutions that I'm doing are really well laid out, right? It's easy to follow. I can tell what's happening as they're going along, right? That's aim for that, right? Aim for that when you're doing your homework, right? Because it's time now. Engineers are known for being anal and being like concise with all this. It's time, right? I know some of you are that way at this point. Some of you I definitely know are not. You have really ugly work, right? It's time to switch over. It's time to do it. We're gonna be grown-ups. We're gonna learn how to do it. Acceleration of function of time, right? So in this case, they give us this acceleration of function of time. It's 30 plus 2t, right? I always like to start, so at this point, what I would suggest you do is you look up in your notes, how do I deal with acceleration of function of time, right? This one's easy enough to go along, right? It's to kind of derive as we go along, right? That's just equal to dv dt, right? The acceleration is the time rate of change of the velocity, right? So then I get everything on that side. Then I put all my t's on one side. 30 plus 2t dt is equal to dv, right? And I got those little dt, the dv's, so I got to integrate to solve these. Give myself a little bit more room, right? And this thing is going from 0 to a time t. I don't know what the time is. And I'm going this from 0 to v. Right? And then you just carry out that integration, right, at this point. Right? I could take the integral of 30 plus 2t, right? And I take the integral of dv, which is going to be v minus v naught, is what the right-hand side is going to be. So we just carry that out, right? I swear to you, I'm sure I put this on my calculator the first time I did it, right? Your calculator will do this. I'm totally fine with that, right? It's an easy one to do, right? But there it is, 30t plus 2t squared over 2. That would just be t squared at that point, right? And that's equal to v. That is now, right now, that is in its form, its velocity is a function of time, right? Because I got v on this side, my v is equal to something with time on the left-hand side. So that's it. When we talk about velocity as a function of time, there it is, right? There's velocity as a function of time, because t's are on the left-hand side, v's on the right-hand side. If I put in t's, I get v's, right? And so that's what the kind of definition of a function is, right? So at this point though, right, I'm accelerating like this until I hit 400 meters per second. So at this point, I could set this equal to 400, right? I could set this equal to 400 and solve for t, right? And so I say v of t is equal to 400, and then what I did there is I put that sucker in my calculator, right? And I got t is equal to 10 seconds. Right? So that acceleration portion is t equal to 10 seconds. Totally fine. If you go through and you get to this point right here, right? You just, and you can't just leave everything as complete variables, but put in all your knowns at this point and then set that thing equal to 400. And then that's all the work I need to see when you're doing your solution, right? You don't even have to say, oh, I used a calculator to determine what that t is. But but that's exactly what I did. I set this equal to 400, right? And I solved for the unknown. The only unknown in that equation is t. I used the solver on my T89. I said F2 solve, 30t plus 2t squared over 2 is equal to 400. Solve in terms of t. Boop, grrr, it pops out. T equal 10 seconds, okay? Which is great, okay? I'm not gonna, I will say that a lot through here. I really, really like calculators. Okay. All right, so at that point, I got velocity as a function of time. I need to keep going. I need to get what my position is, right? I know how much time it is. I need to know what my position is at the end of my position is at the end of the first acceleration. What am I after here? I'm trying to find the total distance traveled. I forgot to mention that before. I need to find the total distance traveled. So I need to know how much distance I've traveled in the first 10 seconds. And so I come back to this is, again, I'm still in the acceleration of function of time portion of this, right? And so I say, hey, my velocity is equal to ds dt. It's the time rate of change of the position, right? So I do the same thing. I take my velocity as a function of time and I multiply that by dt rather is equal to ds, right? I know what my velocity is a function of time. That's this right here. Right, here's my velocity as a function of time. So I take that and I put it right there, right? So that's what we do here. And then I integrate, right? So my velocity as a function of time is gonna be 30t plus 2t squared. I'm gonna keep it that way because I'm lazy. 2t squared over 2. It's actually more work to do it that way. Not dropping those 2's. Yes, right? I integrate. Ooh. dt, I'm missing the dt there. I'm gonna integrate on this side, integrate on this side. This is going from, now I know these things, this is going from 0 to 10 seconds, right? Because this is that 10 seconds we found before, so I can actually put it in a definite integral. That can put that in as a 10 second, and this is going from 0 to, we'll call that S1. How far it's traveled after the first phase. Okay. The right-hand side just becomes S1 minus 0. And then the left-hand side, I didn't actually ever calculate. I just put it in my calculator, right? I put this, you could do definite integrals in your calculator. You could say, do the integral 30t plus 2t squared over 2, comma, t, comma, 0, comma, 10, and it'll do the definite integral, and out will pop the answer right there, right? So this ends up being equal to, S1 ends up being equal to 1833 meters. Okay, so now we know the first acceleration portion took 10 seconds, and then it has traveled in that first acceleration portion 1833. Okay, so now we're done with that part. Okay, that's the acceleration part. Now let's go on to the deceleration part where the thing starts slowing down, right? deceleration. Okay? This is a function of velocity. Excel, a function of velocity. Okay. Right, and now this thing, again, what do I do at this point? I need to look up what we do with acceleration, a function of velocities. Okay, and in fact, we're dealing with positions. So before I did have this little shortcut that we can do when we're dealing with positions and how to go velocity is a function of position. And we're going to use that little shortcut as we go through here, right? And you can kind of look up and see that that's in our notes above how we handled that, right? And what it was this. We said acceleration a function of velocity, right? That's equal, we're going to use the chain rule. That's equal to dv dt. We use the chain rule. This is dv ds, ds dt, right? This is just velocity. So this is dv ds times the velocity. Okay? And then so I put all the ds's and all the v's on the other side. So my ds ends up being on the left, and the right-hand side, I get v over acceleration function of velocity, dv. Everything with v's go on one side, everything that's not v's go on the other side. So in this case, this is what I end up with. Okay, so I kind of got out of the time domain. I kind of jumped out of that. See, there's no times floating around here anymore. Right, that's the kind of the shortcut. I'll show you, you can do it if you leave time in there. There's another way of doing it. That's what's on the next page, but this is using that shortcut. Okay, so at this point, right, I plug in all my known things and I integrate. So this guy's going from S1, what we found before, right? Because it has a position already. It has S1. I could put in a 0 there, and then I'd solve for how much it traveled since the last one, right? Or I could put in what my S1 is that I solved for up above at this point, right? But just see, if you put in a 0 there, just remember you have to add on that 1833 or whatever that we found from, we have to add on this 1833 before. Or you can put it here as part of this definite integral, right? And then what we're after is actually this. We're after this variable right here, our SF, right? And then this thing is being integrated from V1 to VF. Okay, which we actually know these ones, right? I guess we could plug these in. Well, I'll do one more time here. All right, so then we can actually plug in variables here at this point too, right? So let's go ahead and do all those things. This is going to be 1833. That's going to go to SF. This is going to be ds. I'm carrying out that integral. This side here, this integral is going to go from V1, which we solved before, which is 400, right? And this thing's going to 100. And then it's going to be the V over, now I just put in my actual equation for AV, right? I put in my actual equation for AV. That was given to us, right? There's my AV equation right here. If you want, we can make it clear that that's going in. That's going in right there, right? It's going to be a negative because it's decelerating. Black, negative 0.003 v squared dv. Right, and I put it in just like that. That v that's up at the top, right? This v that's up at the top, that's the same v that's in my equation right there, right? That's the same v. And this just becomes one new big function, right? So that v and that v cancel out, and then you carry out that integral, right? At this point right here, right? This is all I would want to see. That's all I need to see. And then you can give me the answer, right? This you could put into your calculator, exactly like this, into your calculator. Right? You can even set it up in your well, I see you keep saying your calculator, assuming it's a TI-89 or above, right? If it's TI-83, boo. You should be ashamed. Right? But I don't know what you could do with that. I will say I'm not sure what you could do with the 83. I think it'll carry out 83 and 84. They'll do integrals, right? It won't look as pretty. In the 89, you could actually set it up where as a solve function. You could say solve, put an integral on one side, and then have the integral on the other side, and then say solve for this unknown variable, and it'll actually carry that out, right? You don't have to, that's an advanced maneuver, but at least you could carry out this integral. That's just going to be SF minus 1833, and then the right-hand side, oh, I don't even remember how to do that. Is that log or something? We have 1 over a variable. Natural log, who cares, right? Who cares? Let my calculator do that shit, right? And you carry that out, and then carry out that definite integral, and then it'll tell you that SF is equal to 2295.1 meters. And there's our final answer. Okay. And that was using the shortcut, right? I went right from acceleration a function of velocity to velocity as a function of position, and I left out the time component. Okay, so this is what I'm saying. Like that's why I think this first part of this class is more difficult, because there's so many different routes you could take to get to the answer, right? And so this one, this one's pretty straightforward. There's no other real routes here, but here there's a couple different routes you can do. You could leave time in there and figure out the amount of time that it takes, and once you figure that out, then you can go, keep working your way around. Or there's this shortcut that you can go that goes right from velocity to position and lets you skip the time domain. Okay, I think in your skeleton notes is this. Is that right? Did I give you that if you're in skeleton notes? I think this is here. This is how you would do it if you didn't take the shortcut. Is that correct? Right, I have it in there. So if you want to look, you might make note that that's what this is. This is the same problem. It's just we're not taking the shortcut. And it's a lot longer if you don't do the shortcut. Not a lot longer, but a bit longer, right? So that in that case, right, you isolate again. This is your acceleration. That's just dv dt. I'm not using the chain rule, and so I put all the t's on one side. So this t comes over to this side, and I put all the v's on the other side, and I do that, right? And so then I have this is going from 10 seconds to an unknown time. This is going from V naught to V, where this is going to be 400 and that's going to be 100. And you can work your way around and you can solve for how much time it takes. That's what I've done here. Then you take that time and you put it back in and gives you my velocity. Once I figured out that velocity function of time, I then integrate and then I can get my position. So it's just one extra little step along the way. But that also gives you the same answer if you do it that way. As I'm saying, there's a couple different ways to do it. Is one way better than the other? Not necessarily, right? Whatever makes sense to you. Okay. Any questions about the 1D stuff? So now I think we've gone over enough stuff. You should be able to do your homework, okay? Also, there's hours in the Learning Center at this point. Anika's in there. I think, what day is today? Wednesday. I think he was starting the afternoon today. I think she's in there afternoon today, afternoon tomorrow, and afternoon of Friday, okay? And she's waiting to work with you on these problems. Otherwise, she's gonna be bored just staring at a wall in there. Use these resources. We've given them to you for a reason. Okay. And then has everybody submitted the homework through Gradescope yet? Okay. I still don't know if it works. That's what I just wanted to, because it's supposed to be linked through, and I just don't know how well it's doing. Okay. Curved motion. All right, so we're going to have 3 different coordinate systems in curved motion. Like I said, it's all just going to be multiple 1D problems. So we're going to have 3 coordinate systems, and I used to be a huge hater of the polar and cylindrical. You haven't seen normal tangent before, but polar, like whenever we move into polar, I'm just like, boo, this sucks, right? But there are certain problems where it would be impossible to solve in Cartesian coordinates, and you need to do polar coordinates. Right? Some orbit would be a perfect example. Things that are going into orbit. It'd be very difficult to solve that if you tried doing that all in Cartesian. So there's reasons why. Okay, so Cartesian is all of our favorites. That's the x, y, and z. Normal tangent's a new one. It talks about coordinates that are normal to the path and tangent to the path, and polar cylindrical are similar to normal tangent. And actually, they converge when we talk about circles, but we'll get into that. So we're going to do Cartesian coordinates first. Right? And we're going to deal with acceleration and velocity and position in each of those coordinate systems, and we'll go from there. So Cartesian coordinate system, right? Let's do that one first and see what happens to velocity and acceleration. So I've got a path right? Something's traveling along that path. It's going from one point to another point, right? And I have my Cartesian coordinate system is X, Y, and Z. I have the X, Y, and Z direction, right? And if I want to talk about the position of that particle, then I have to give its X, Y, and Z coordinates, okay? And so when we talk about position, again, R stands for position. Things are becoming vectors now, right? Because now we didn't have vectors last time because everything was just 1D, but now things are gonna be vectors. So our vectors are gonna be, we're gonna do this, we're gonna call X in the I plus Y in the J plus Z in the K, right? We're gonna call them out like that. You can also, right, because that'll tell us where that is located, right? How much in the X, how much in the Y, how much in the Z. That'll tell us where it's at, right? And then the I, J, and the K refer to each of those different directions, okay? You can also write this R can also be written a couple different ways. It can be X, Y, Z, you put them in these square brackets. Later on in the semester, we'll switch over to doing that, right? That also means the same thing. This is in the I, J, and the K direction, respectively, right? You could also see them, sometimes you see them, that's a row vector. Sometimes you see it as a column vector. X, Y, and Z, like this. There's some reasons why we don't write them like that. At least in the derivation, there's some reasons why we're not dealing with them like that. You can do either one. When you solve the problem, it's okay to have them in those formats, okay? But when we're doing this derivation, we have to do the I, J, and the K, okay? These I, J, and Ks, I put a caret on it. J and the K, okay? These are unit vectors. Unit vectors. They have direction, but no magnitude. Or magnitude of 1, I should say, but. There's pointing in the directions. The carets just tell us that there's pointed in the 3 different directions. Unit vectors. All right. Okay. So this thing is going to go from one point to another, right? So after a certain amount of time, that position is going to change. I don't want that. I want that. You motherfucker. Quit doing that. Quit doing it. How do I do a draw? How do I do? Okay. There we go. All right. So this is going to be R of T plus delta T. And again, if I'm talking how much that changes, that's this vector that's coming down like this. And that's going to be delta R. Is how much that changes from one point to another point, right? I kind of briefly derived this before. So we come down here and we start talking about velocity. What does velocity mean in this direction? Velocity in this coordinate system, it's pretty straightforward, and then I'll explain afterwards why we do this complex derivation of this, but that's going to be dr dt. It's how does that change? How does my position change with respect to time? Well, my position is, in this case, in this coordinate system, is x in the I plus y in the j plus z in the k. Right? That is what my r vector looks like. And how does that change with respect to time? Right? So I'm going to take, I need to take the derivative of this vector right here. Right? And so this is where the product rule, as it's called, when you take the derivative of something multiplied by something else. So x is something, I is something else, and so they're multiplied by each other. So I have to take the derivative of something multiplied by something. What do you do there? That's the product rule. Remember the product rule? What is that? Yeah. Take the derivative of the first thing and you leave the second thing alone, and then you take the derivative of the second thing and leave the first thing alone, right? So we have to do that here. So that this thing blows up on us a little bit. So this becomes derivative of the first thing would be dx dt times I. I left the second thing alone, right? And then I go ahead and I do this and I call the next one and I multiply this by x di dt. Take the derivative of the second thing, leave the first thing alone, right? That's all just this first term, right? So I keep going with it. Now I go plus derivative of the first thing, dy dt in the j, plus y times dj dt. That's the second term. Then the third term now, we take the derivative of the first thing, dz dt in the k, plus z times dk dt. Okay. So now that's what my velocity term is going to look like in this coordinate system. Now, this is interesting. How does this coordinate system change with respect to time? How does I change with respect to time? Doesn't, right? It's just stationary. It's just sitting off to the side, just holding steady. Path is moving, or the particle is moving along a path. It doesn't change. It stays the same. So the time rate of change of these three terms, di dt, that's 0, right? dj dt is 0, and dk dt is 0. And that's kind of obvious that that's going to happen, right? Like it should just be, well, if I'm talking about velocities, it's just going to be, so this simplifies down to this here, right? It's just uncoupled. It's an uncoupled system. If I'm talking about velocities in this coordinate system, I'm going to say, how is x changing with respect to time? And that's going to be in the I direction. How is y changing with respect to time? That's going to be in the j direction. And how is z changing with respect to time? That's going to be in the k direction, right? And so it's just going to be vx in the I, vy in the j, and vz in the k. And that there isn't these other terms floating around. You're like, well, why the hell did we go through that big thing? In a few minutes, that's not going to be the case, okay? When we deal with normal tangent and polar coordinates, our coordinate system is actually going to be on the path, and it's going to be changing with time. It's kind of weird to think about, but your coordinate system is going to be attached to that particle, and it's going to be moving with the particle, right? And again, it gets complicated, but there's some reasons why we do it that way. But when we get to that point and we're taking the derivative, we're going to do the same thing where you take the derivative and the product rule is going to apply. And when we take the derivative of the coordinate system, it's not going to go to 0. It's going to become something else, okay? Do you guys notice how I talk to this side more than this side? I apologize. You can call me out sometimes. One of my sons came into a class once. I didn't know I did it, and then he said, but just a side note, you only talk to that side of the class. I don't know why. Maybe I like this side better. I'm gonna work on it. You're all equal. Okay. So then you do the same thing. So that's my velocity in this coordinate system, right? And we'll do the next for acceleration. So the acceleration now, right? Acceleration is equal to dv dt, right? My velocity, right, is now this, right? It's this term, vx in the I, vy in the j, and vz in the k. So you do the same thing. This is going to be equal to d vx in the I, vy in the j, plus vz in the k. And all of this with respect to time. Same thing is going to happen. You apply the product rule, take the derivative of the first thing, leave the second thing alone, take the derivative of the second thing, leave the first thing alone. So this would be vx di dt. I'm just going to do a plus dot dot dot. Right, and this term again is going to 0. Right, you keep going, and then when you do that, you get to this. And the big key finding here is that it's just decoupled, right? You solve the problem in the x direction, you solve the problem in the y direction, and the total answer is those two things added together. You treat them completely separate. It's decoupled motion. What's happening in the x direction does not affect what's happening in the y direction. What's happening in the y doesn't affect what's happening there. What's happening in the z doesn't affect what's happening in there. So it's just multiple 1D problems. So you solve, and then how you do 1D problems? Well, we just talked about that, right? We just talked about how you do the 1D problems, right? And so you just have to do it 3 different times in 3 different directions. Decoupled motion. And again, not the case. When we get to the other coordinate system, it's not decoupled. What's happening in one direction can be affecting what's happening in the other direction. Okay. Oh, we got plenty of time. Cool. Everybody cool? Cool. Decoupled motion, 3 1D problems. Classic example of this, right? I just mentioned this, decoupled motion, right? That classic example, projectile motion, right? This is physics. Again, this is all physics stuff for you, right? So, but we're gonna apply this to projectile motion, right? Let's do a derive kind of projectile motion in these terms. Some assumptions we make. We assume we have constant gravity. We don't, right? But for these projectile motions, for everything kind of basic stuff, we have constant gravity. And if we're talking intercontinental ballistics, then absolutely you should take into consideration that gravity's changing when you're sending stuff up to near orbit on their way back down, right? We're going to neglect drag. Also, not a good assumption to make, because drag really is there when it's in the atmosphere, right? But these are some things that in classic projectile motion we deal, right? We also assume Earth is flat and not spinning. Isn't flat, it is spinning. Just a side note. I'm a believer. Just make it clear. If you guys are looking for a nice movie to watch, you should watch it Behind the Curve. Have you ever seen this movie, Behind the Curve? It's beautiful. Actually, it's really interesting, take on it, right? And it's how us as a society have failed the flat earthers to educate them properly and to have them not trust us, right? And they're like, well, you guys know what they're doing. So they come up with their own science to try to justify their beliefs that the Earth is flat. And then the internet has allowed them all to connect with each other, and that's why it's kind of exploded, and why that people have taken off on this. They're like, oh, but throughout the whole thing, it's really interesting to see, right? And it ends with this really cool scene where they come up with their own experiment across a lake, and they have this light set up on one side and a light set up on the other side, and they're like, we're going to prove this is not flat because we're going to hold the light up 7 feet, and on the other side we're going to hold the light up 7 feet, and we're going to be able, or you're going to have a hole that the light has to go through at 7 feet, and you'll only be able to see it, if the Earth is flat. And right at the end, they're like, they can't see it, and they're like, what's going on? They're like, we'll raise it up a little higher, and he raises it higher. And then he sees the light, and so they just proved that the Earth had some curvature to it. You'll have to watch it. Yeah, he goes exactly right. Then he goes, huh? And then it ends. Right? It just stops because he proved that the Earth was round. They also bought a $25,000 gyroscope to show that when Earth is spinning, it's on an axis, and then it was on an axis. So they're like, oh shit. So then they're like, well, it must be some outside sources that are affecting it. So then they encase it in lead, and they're like, and it's still doing it. And they're like, oh, there's something else. And then they put some other fancy material around the outside. And it keeps proving it over and over and over that the Earth is not, in fact.
But if that failed, then they decided to do the alignment.
Yeah, the light. Yeah.
It's screw this side, we'll just do.
Yep, and they just keep proving, but that's the problem, is you can't go into science being like, I know what my effect is, and I'm going to design experiments about getting that and proving that. You do the experiments, and then you follow what the evidence is, and that's where we failed them, is they're coming in with this preconceived thing. I know a couple flat earthers. I do. I choose not to talk to them about this aspect of it. All right. So gravity's acting down like that, okay? And so, right, we deal with these things in multiple directions, right? It's decoupled motion. What's happening in the x doesn't affect what's happening in the y and so forth. So we're gonna do this. We're gonna drive for the x direction and then the y direction, the equations, okay? All right, so these are constant accel, x direction. There is no acceleration, right? And in fact, acceleration is equal to 0 in this direction, right? There's nothing causing acceleration in that direction, but it is constant acceleration, right? And the equations for constant acceleration to get to velocity this is just equal to, I'll set this equal to a up here, is just v naught times x plus acceleration in the x direction times time, right? And we just said this acceleration in the x direction, that's 0. And so the only component we have left is v naught in the x direction, right? And so usually, I forgot to mention this before, these projectile motion type problems, what they usually start out with is we give it an initial velocity and an angle in which it's being launched, right? So or thrown or whatever it is. That's kind of the basics that go into this, right? And so based off of v naught, I can figure out what component is going in the x direction and what component is going in the y direction. The component going in the x direction is v naught x, right? And the component going in the y direction is v naught y, right? And so I can do my trig there, and I can actually put in a value for v naught x, and that's just going to be v naught cosine x, or cosine theta rather. Cosine theta, right? And so that's what we get for this. There's my equation for my velocity in the x direction. Right? It's constant, right? There is no acceleration term because acceleration in that direction, especially if we're ignoring drag. If we have drag in there, that's not the case, right? If there's drag in there, it's going to be things get a little more complicated. A function of velocity in the x direction. But in this case, right, no acceleration. It's going to start out at v naught cosine x. It's going to stay v naught cosine x. Okay, the position, right? Again, constant acceleration. For constant acceleration, my position equation, x is a function of time, is going to be x naught plus v naught x times time plus 1/2 axt squared, right? And so again, no acceleration. That term goes to 0. Right? In this problem, in this classic projectile motion problem, it's starting out with a position of equal to 0. So that guy's going to 0 in this problem right here. And so the only thing that you're going to have is the velocity times time, right? The velocity in the x component times time will give us the position as we go along, right? And that's some pretty basic stuff right there. Take velocity and you multiply it by time, it tells you position, right? That's some pretty standard stuff. So there's not much going on in the x direction because there's no accelerations, right? In the y direction, though, we have gravity, right? And gravity is going to be at play here. So this is constant acceleration. AY is equal to negative g. Equal to negative g. Right, so my Vy as a function of time is just going to be V naught y, the initial velocity in that y direction, plus AY t squared. Oh, no, sorry. Got ahead of myself here. Just AY times t. And then again, this V naught y, we can get that right out the beginning. So this is going to be V naught times sine of theta. Right? And so then we get this. We'll use these in some examples in a little bit. Vy is a function of time. It's just V naught sine of theta. That's the V naught y initially. And then minus gt. And then the minus there is important because the way we set up our coordinate systems up was positive. And so that acceleration is acting now down in the y direction. So it's negative g in there. Okay, so that's my Vy as a function of time. So then we just have to go to position, and be ready to do some problems. Position here, y as a function of time, is equal to V naught plus V naught y times time plus 1/2 AY t squared. Again, starting out without a position, or without an initial velocity. That guy goes to 0. V naught y, we have that's V naught times sine, and then AY is just G. So this guy just comes down to this. This is all review to you guys at this point. So there's my y position as a function of time. Cool. Okay. So what we'll do next time, and we'll start out with this example right here. We have an object that's kind of traveling to the right at an initial velocity, and then we have a projectile. We have some gravity acting down like this. We have a projectile that we're going to launch that's going to try to hit particle A as it's moving along the way, and we'll go from there. So that's one of the problems we'll do. A little more complicated because you've got two objects floating around, right? And we'll do this. We'll quickly do kind of just a classic projectile motion type problem, and then we'll move on to angular motion, right? Things that are rotating. We're gonna have thetas and omegas and alphas floating around. You may remember doing this at some point. Those are all kind of acceleration in terms of like angular motion, which are gonna lead us to normal tangent coordinates, which then we'll go on and do a bunch of problems with those. Those get a little more exciting than just projectile motions. Like we're gonna have somebody jumping from a bridge attached to a rope and stuff like that that kind of like do a big swing and stuff. We calculate forces and stuff like that. So, and we'll also drive orbits, which is kind of cool. All right. I guess we'll call it there. And break. I gotta come up with something fun to win.